Today we're going to be talking about RC circuits, and RC stands for resistor capacitor. So these are circuits that have then a resistor and a capacitor in it, and a voltage source so that we can charge these things, and then they become kind of useful in their interesting way that they charge and discharge. And because of how they charge and discharge, they could be used for things that have kind of like variable or intermittent type actions. And that would be like your windshield wipers, timing of traffic lights, pacemakers, camera flashes. All right. And again, it is useful because of how the voltage and charge on capacitors take time. So they charge over time. It's not instantaneous. And we're going to see graphically what these voltage and charge changes look like. All right. So the first thing we're going to take a look at here is the change when we close a circuit. So this is the charging of an RC circuit. All right. So just imagine you have a resistor or capacitor with a switch and a voltage supply, and you are going to close the switch. Let me move this up a little bit so we can see a little bit more at the same time. So here's our example right down here. So here's our voltage, and so this voltage of battery right here. This is our capacitor. By the way, a capacitor schematic symbol has two lines that are of the same length, unlike a battery, which has a long line and a short line. Remember, the long line is our plus side, and the short line is our negative. And then here we have a switch that we're going to close. And right when we close it, what's going to happen? Well, when we close this, current is going to want to flow, and we will get electrons that will flow this way in the picture, and they will flow, right, it's trying to complete the circuit, and electrons will flow here and build up on this plate of the capacitor. Now, as this charge builds up here, then the electrons on the other side are going to want to run away, okay? They are going to repel, and electrons are going to leave this side, and that would leave this side of the capacitor plate positive as those electrons go to the other side of the battery. All right, so that's the mechanism right there. And at first, the flow is going to be really great. These electrons are rushing to this blank space, all right? And we can imagine, though, as this negative starts to build up here, that these electrons are going to be starting to repel here. And this side is going to have a hard time pushing all the electrons away because this positive charge is going to start to attract them. So at first when you close that door, there is a giant rush, okay? And then things start to slow down, okay? So as this capacitor starts to build a negative and positive, also realize, right, it's looking like a battery. It has and look, it's opposite. It's getting a plus and a negative, and it is starting to have its own voltage, all right? And we can see now, let's look at this graph right here. So this is, in fact, capacitor voltage right here. And we can see that it builds really, really quickly. The voltage builds, and then it starts to level off here, okay? And we're going to talk about the time periods in just a minute. But you can see this kind of exponential, and then it starts to become what we call, you see the word here, steady state. So it's pretty much even. And this is then, it's the maximum amount that you can build. Now, how much is the maximum voltage this battery would this capacitor would end up with. That actually would be equivalent to what the battery is. Think of it almost like if you had a case where you had something like some kind of a pump and it had a high pressure, and you opened it up, and this could be like water or it could be anything, then it's going to give its pressure away, and now this is all pressure, and now these things, when this voltage becomes what the battery was, then the battery is no longer useful anymore. Okay, and it can't push anymore. So you've created this maximum voltage, which was the maximum voltage of the battery. Now, the voltage of the battery, which here in this diagram is labeled VB, your book likes to use EMF. And EMF stands for electromotive force. And we didn't spend much time talking about it or at all, but you can read about electromotive force. Basically, it's the effective voltage of a battery, realizing that a battery has some internal resistance and all kinds of things going on. So it's this wonderful curly Q E that we can symbolize that. And for our basic purposes, think of it just the voltage of the battery. So depending on your source, you may see our formulas with the E in it, or you may see voltage of the battery. All right. So again, and here in this graph, I think they used voltage of source. All right. And that will be then your maximum voltage. All right. We can also see at the bottom down here that the voltage of the battery produces is going to be equivalent, or the sum of the voltage the resistor has and the voltage of the capacitor. So those two together will be taking that voltage. So just like before, if we had a bunch of resistors in series, you would add up the voltages of the resistors, would add up to the voltage of the battery. And we can say that here now, except for we have a resistor and a capacitor in series. Now, if you want to know what the voltage of the resistor would take, we just do I times R, the current in the loop times the resistance of the resistor. But if you want to know the voltage of the capacitor, we know that that equals Q divided by C. And so you can do that. All right. Let's take a look at our formulas then here. So we have the voltage of the capacitor equals then the voltage of the battery, or EMF of the battery, times the quantity 1 minus natural log to the negative T over RC. We're going to get into this, but this is a natural logarithmic pace where the voltage climbs until it hits this maximum. Okay, so we know something about whatever this is. We know that this number is going to start off big because at first our voltage is 0. So we can't, our capacitor is not going to equal the voltage of the battery at time 0. In fact, it's going to be 0. And the only way we get this to be 0 is if this factor is basically a complete 1, and then 1 minus 1 is 0, and we multiply, and you'd get nothing. And as this grows, we can see graphically the capacitor voltage grows, we're going to subtract less and less away from this total EMF or voltage. All right, let's look at this second. Actually, let's look at all of this real quick. So we have a lot of graphs, and including ones that are overlapping here. This should make sense. This red graph is our charging. So we can see we're charging, and I think the area under this graph then is going to be our Q. We're reaching some maximum charge that we're building up here. So Q, we have another formula with a natural log here. So Q, we said, equals, right, C times V, and that V is going to be the voltage of the battery. If this is our Q max right here. This right here, our Q at any time is going to be our Q max again times this same product here. So 1 minus the natural log of minus T over RC. And so Q changes proportionally as your voltage changes. So again, as you close the little switch, you're going to do most of the charging early on, and then just near the end, you get a little bit more charge built up here. All right. Now let's look at this next line here. This is the current in the circuit. So, or how about say the current from the battery, okay? Or current in circuit. And what do we see happening there? Well, when you close this door and there was no resistance at all in here, well, okay, sorry. We had resistance of this resistor here. That's our only thing that was resisting flow. We had some I max, and so you can see, in fact, how do you find out that maximum current is, we see here, you take the voltage of the battery and divide it by the resistance, and then you would know the current, because this is the only thing here. The resistor was the only thing that was resisting flow at first, and so you have what you have calculated as the maximum current that you could have given that resistor and that voltage of the battery. Then as time goes on, very quickly that current decays. The amount of current that you have goes down quickly as this charge builds up, and it builds up basically an internal resistance because, of course, electrons don't want to go towards a large body of electrons. All right, now look at that formula here. So we have I equals VB over R. That's basically right here your I max. Okay, so I at any point in time equals your I max times E minus T over RC. So now we don't have that 1 minus. All right, so this is a decay. This number gets smaller and smaller, all right, as this logarithmic scale decrease. All right, so we have exponential decay of current that is through that circuit. All right, what else do we want to say here? And yeah, so we see here that current decreases, charge increases here. So here's the factors at time 0, and here we can see as time becomes infinitely long. And infinite, by the way, we reach infinity very quickly. In fact, you can see down here, it says the time is not in seconds down here. The time, it says RC, 2RC, 3RC, 4RC. So what is that all about? Well, and then up here we can see they just put a T. Usually we use the Greek letter tau for this thing called a time constant. And usually by the time you get to 4 or 5 time constants, you're maxed out. You've reached no current, you've reached full charge, and the capacitor has the voltage of the battery when we get done with this. All right, so let's take a look at this thing called the time constant. All right, again, you'll see just a capital T for it, or we can give a Greek tau for it. So the time constant is just R times C, and it ends up being a measure of how quickly a capacitor gets charged. And it turns out it is actually the time required for a capacitor's voltage or charge to reach 63% of the maximum. Now, where does this 63%? Because that's kind of a weird thing. Why would we care about that? Okay, or how does this become relevant? So here we have our natural log e to the negative 1. And in case you have forgotten any kind of math, oh, let me do a little side. If you've got any kind of math, e to the 1 is around 2.7. You know me, I don't remember numbers. So that's natural log e. And e to the negative 1 turns out to be 1 over 2.7, which is then 0.37. All right, so you get a natural log e to the minus 1 is 0.37, and that is where we're getting the 63% from, because that's all. So we end up subtracting this factor. You're going to see in just a second. All right, in fact, so in our formula, we had our EMF 1 minus e to the minus 1 t over RC. Now, if I make this T equal to RC, if I make these numbers the same, whoops, I forgot my little minus sign here. Oh, this is different. So this one, I've put it on the outside. Okay, so if I put a T over RC there, and these numbers are the same, then it's just going to be 1. All right, and so what happens then is we just have e to this -1, which we know is 0.37. So we get 1 minus 0.37, and then we get 0.63 times e. And so basically we have 63% of our voltage, okay? So the capacitor will be at 63% charged, and again, that's the same because it's going to get the charge from the battery. That would be then 63% of the voltage of the battery. All right, so here's an example where we can just see it with numbers. So if you have a 200K ohm resistor and a capacitor that is 3 microfarads, then let's calculate the time constant, tau. So we're going to have 200 times 10 to the 3, right, times our 3.0, and don't forget the micro, times 10 to the -6 farads. And if we do that, by the way, let's take a look at these units real quick. Oops, I didn't even put in a unit. What was it, bad? So that was ohms, right? And so if we take a look, our ohms, if you wanted to know what the base unit of ohms is, volts per amp, and farads are coulombs per volt, then that will get us somewhere here. And so we should end up at 0.60. And what are our units then? We see the volts go away, and we're left with coulombs per amp. And you go, what are coulombs per amp? Well, an amp is a coulomb per second, and so in the end, we do get time. We get 0.6 seconds. All right, so there's an example of our time constant, okay? If R decreases, so if we have a lower resistance resistor in our circuit, then our tau, our time constant, is going to decrease. And if our time constant decreases, then we will reach charge quicker. All right. So if you want a quick charge of your capacitor, but that we're going to find out that also will mean a quick discharge, then you can make a combination here where you would have a lower resistance resistor. Okay. Now, let's keep talking about what's going on here. Since all circuits have some resistance, by the way, a capacitor can never fully get charged, and it can't be charged instantaneously. All right, because there always is this time constant. All right. How about the voltage of the resistor? At first, we know if there's nothing else happening in the circuit, the resistor would get all the voltage of the battery, right? There's only one thing in that circuit. If you have a battery and you have this, and it's almost like, since the capacitor didn't do anything yet, right when you close the door, then whatever the voltage of this has to be the voltage of this. All right. We can think of Kirchhoff's laws for this, really, right? That each object, the sum of all the objects, has to equal this voltage, or in other words, it all adds up to 0. Actually, this is one, like a positive voltage, and then this would take a negative voltage. All right. But after a while, the capacitor starts to take some voltage. The voltage in this will grow and grow as the resistance of this grows. All right. So if we want to think about the voltage of the resistor, it at first would be the voltage of the battery, and then as this capacitor grows, it's going to become less and less. So it would be equal to the voltage of the battery minus the voltage of the capacitor. And if you then think about the formulas that we have so far, then the voltage of the resistor will equal this formula. So not the 1 minus, all right, the voltage of the resistor that the resistor receives, or the voltage across the resistor as we say it, will decrease as the capacitor charges. All right, so again, exponential decay. I already mentioned this, but here is now a close-up of the graph of the current in the circuit. And again, this is the current you can think of leaving the battery, and it is, right, the current is going to be the current max, and we call that I0. It seems a little weird to call that well, I guess it makes sense. It's the current at right when the door or the switch closes. All right. So of the maximum current that is allowable due to the battery and the resistor, it's going to drop off exponentially. This is a real close-up of that exponential decay. And once again, we can see that it's related to the RC, or the time constant. At one time constant, the current is going to be 0.37. All right, it has decayed 63% at that point. All right, because remember, we said the capacitor charged 63%, and because of that, we only have 0.37% left of the other things. And so here we have, and again, we could figure this out. What we could do the trial, we could put T, you could make T over RC 1, and then you would see that's the case. You'd end up with 0.3. This is just a book example that I thought I'd go through. The capacitance in a circuit is 0.30 microfarad. The total resistance is 20 kilo ohm, and the battery is 12 volts. All right, so determine the time constant, the maximum charge the capacitor could acquire, the time it takes for discharge to reach 99%, so like pretty much done. How much time does it really take to discharge? And then the maximum current. Okay, so in most problems, that is the first thing you're going to do is calculate tau, the time constant. All right, and after a while, they might seem more like, familiar to you, what kind of numbers you're going to get. So we have 20 times 10 to the 3 times 0.30 times 10 to the minus 6, and we will get 0.006, or we could say 6 milliseconds. All right, maximum charge. So our maximum charge, Q0, again, it seems weird at first. I don't know, maybe it makes sense to you. So the maximum charge we can get, we can say, is equal to the capacitance times the voltage of the battery. So this is the most we're going to get. And that basically, again, is our EMF then. So right there. And so we get 0.30 times 10 to the negative 6 farads times 12 volts. And we would get 3.6 times 10 to the minus 6 coulombs. Realize, again, if you want to check your units, things are going okay. A farad is a coulomb per volt. And so, again, our volts cancel, and we are left with coulombs. So that's an appropriate unit. Or you could say this is 3.6 microcoulombs for our answer. All right. How about time for 99%? So let's write our whole charge formula. So we know that Q equals this Q max, or Q0, 1 minus e to the negative T over RC. And let's plug things in. So if we want 99%, that means we want a comparison of Q to Q max, right? So I'm going to bring this over and just put Q over Q max. All right. And then I know that this is going to be 0.99. So I changed my percent to a decimal. All right, I'm taking this really stepwise for you math people or non-math people. And I'm going to bring the 1 over to the other side. So I'm going to say 1, and I'm going to change the sign. 1 minus 0.99 equals, so I'm going to drop that, e to the negative t over rc. All right, and what do I do now? Well, I'm going to get 0.01 on this side, right? But what do I do now? I got an e. Well, this is time for natural log. So if I take the natural log of both sides, that part's going to go away. And so I do natural log of 0.01 in your calculator, and you'll get negative 4.6. Then that's gone, and so I get negative t over rc. And then we can plug in what our rc is, because we did it up above here. So I'm going to go plug in 0.006 right there. All right. And then I'm going to bring it to the left side. So I'm going to end up multiplying. And then I get t equals 0.0276. And so we have 2 significant digits. And so we have 28 milliseconds, if you were going to put it in milliseconds. All right. So not a lot of time to charge this. So 28 milliseconds, and we can see that. And like I mentioned before, that it's pretty much all the graphs you look at go to 4 or 5 time constants, because after that, it's at its max. Max or minimum. Minimum current, maximum charge, and we can see that. So if you see, we could have even not done any math, and pretty much when you see 99%, that's almost fully charged. Times this by 4 and take a look at that. You're pretty much that, okay? So 99% of charge is at about 4 time constants that will occur at. All right, how about maximum current? Our maximum current that we can get, we know I equals V over R, and our voltage is going to be our EMF over our resistance. And so we have 12 over 20 times 10 to the 3rd power, because it was our kilo, and we get 0.006 amps. So current, we have a decay, looks like this. So at 28 milliseconds, all right, that's when we don't have anything left. That's at the top right here. 0.006 amps is our starting current, and at about 4 time constants, we got nothing left. All right, so this would be right when the switch is closed. This is the kind of current we're going to have, and then it's going to decay to pretty much nothing at the end of this. So now we're going to take a look at a discharging capacitor. So this is what happens after we have hooked up our capacitor resistor circuit with a battery and charged it up, and we've charged it up to some voltage, and that voltage should be the same as the voltage of the battery, and we denote it now with a V naught and a Q naught, representing the maximum voltage and maximum charge that this capacitor has, being fully charged. Then you can either remove the battery, or that's what the picture shows here, that we don't even have a battery now. And in fact, our capacitor is, in a sense, going to act as a voltage source when we close the door. So we're going to look now, and we're going to think about, as you close the switch here, so when time is 0 is right when the switch is closed, what's going to start to happen? Well, remember, we had our one side of our capacitor, has a big negative charge, and the other side is all positive. And remember, those are opposite to what your battery was at some point. And now if you close the switch, it's going to act like a battery, so the negative end is going to release electrons, and so electrons are going to flow in this direction as here, and try to go towards the positive end. So we're discharging the capacitor, but we have a resistor here. All right. Originally, right, if there was a battery there, that battery would look like this, plus minus. Wait, sorry, plus minus that would have charged this. So notice this is in the opposite direction, and this would have created a current in this direction. So when we discharge the capacitor, the electrons are flowing, and therefore the conventional current is flowing in the opposite direction here. And at first, because there's a big buildup of charge, there's going to be a large current, and this originally had a high voltage, and this voltage of the capacitor will drop. And so we get, so from high voltage, we get to look at this graph here, and in fact the voltage is going to drop exponentially. So we have exponential decay of voltage as this loses its big plus minus difference, on the plates, as well as the charge that it's holding is going to fall at the same rate, and the current. So all of these are all in the same direction, and it's down. So there's decay in current, charge, and voltage as the capacitor dissipates. All right, and just like we saw before, our voltage is going to fall, but now it's the other end. So the voltage will end up being in the time constant down to 0.37 of the initial voltage. So here in the graph, here at 1 tau time constant, we're down all the way to 0.37 or 37% of our initial top value of V0, Q0. All right, and what am I missing? I0. All right, and we can run through that. Okay, what is there else to say? I think that's pretty much it. So it's nice that this is all in a line like this. Oh, and again, the voltage across the resistor is going to be the same as the capacitor because we don't have a battery in there. And remember Kirchhoff's laws. So in fact, Kirchhoff's voltage law, right, states that V1 plus V2 plus however many you have should all add up to 0. And so now our two things that have voltage is our capacitor and our resistor. And as this thing starts to tank, this thing grows, equal and opposite, and so that they have to add to 0. Okay, so that's kind of interesting. All right. So let's take a look at a problem here. Again, just a book question example. If a charge capacitor of 35 microfarad is connected to a resistance of 120 ohm, how much time will elapse until the voltage falls to 10% of its original value? So these are all very typical problems. We already saw 99%, and they always want to know or half a value or that kind of thing is very common. So the voltage of the capacitor equals the initial or full voltage of the capacitor. So before you open the switch, or close the switch, excuse me, open the floodgates. And so we have this formula. Again, we are going to bring this over, and we want a comparison of the capacitor's current voltage to the max. And we're going to say that value is going to be 10%. So we can turn that into 0.10 equals e to the minus t. And then we need to put it over RC. So we should go to the side and calculate what our time constant is. And that would just be 120 times our 35 times 10 to the minus 6. And that would give us 0.0042. All right, and then we take and put that in there. All right, then we love the fact that we can do natural logs again. So we do natural log, those go away. And then the natural log of 0.10 is negative 2.30. Then we're left with negative t over 0.0042. And then we just solve for t. And we get 0.00967. And that will turn into 9.7 milliseconds. All right? All right. The second question is just a thought problem, really. It says a bulb in an RC circuit. In a circuit with a light bulb, voltage source, switch, and an uncharged capacitor, describe the behavior of the light bulb from the instant the switch is closed. All right, until a long time later. Now, a long time later doesn't really have to be that long because these time constants tend to be pretty short. But if we're going to be describing what happens to the light bulb will behave according to if it's getting current or not. So we really can look at what's going to happen when we close this. So the moment the switch is closed, the circuit's going to have a high current as the capacitor has not had a chance to charge, and the bulb will be at its brightest. As time goes on, the capacitor receives more voltage and the rest of the circuit less. After the capacitor has the same V as the battery, the bulb receives no current and is out. So in this case, we have a bulb in a circuit, and we have a light bulb. Let me draw Mr. Light. So we have a light bulb here, and we have our voltage source. We have a switch, and then we have our capacitor. And so the question is, right when we close this, what's going to happen? Describe what's going to be happening to this light bulb as time goes on. So right when we close the switch, we have a powerful battery, and it's going to definitely want to send electrons and start zooming electrons to this capacitor. Remember, right when we close the switch, we have high current. And we have high current because those electrons can flow easily. And at the beginning, the resistance of this, so I is high, the resistance of the capacitor is really low, and so we have a high current. So at first, the light bulb is going to be bright. Okay? As time goes on, as we know, as the charge starts building up on the capacitor, then there isn't going to be a reason for electrons to flow. As this side starts to become negative and the other side starts to become positive, we are definitely going to get low flow. Basically, this light bulb is the resistor in the RC circuit. And as time goes on, this will consume the voltage, all right? So the capacitor will consume more and more voltage, and this resistor will get less and less, this resistor slash light bulb will get less and less of the voltage and low current. So the light bulb will exponentially, decay in brightness. All right. And it should go out, right? When would you predict it to go out? The best we can say is probably in 4 to 5 time constants that should be out. All right. Then you could remove the battery, and then it would do the same thing going the other way. Okay. All right, so why do we have these RC circuits? Well, what we'd like to do with this, and what we see with this exponential decay and this variable filling, is that we can create voltage pulses, and so that might be interesting in some uses. And we see this a lot with any kind of blinking light that we want to make, or windshield wipers, anything that happens intermittently. And so apparently we can set this thing up with some kind of a gas-filled tube that causes a breakdown, so that at a certain voltage, all of a sudden it's no longer able to carry current in the same way, and that will be our trigger. So here we have it at time 0. We are going to hook everything up, and the battery or voltage source is going to charge. We see here we're going to charge our capacitor, and we see that slope that we know we can use the formulas to figure out. Then all of a sudden it hits this peak, and this peak is where there's a breakdown, and right here then all of a sudden it's like that the battery has basically been disconnected, and then it's like all of a sudden it's our capacitor discharges. And at this low value, then we get where the gas-filled tube again functions, and then it can recharge. So we get this charging of a capacitor and discharging of a capacitor, and it creates this sawtooth shape that these RC circuits are famous for. And then, so we have these periods in time where the capacitor is providing then a voltage and current source, and we see that in the graph below. And so this can be creating our pulsing, and we can see here this is a common way that a blinking light can be set up. We have a capacitor that's in series with a neon light here, and at first, if you have again this voltage source, our battery, it's first going to go, those electrons will take the easiest path. They don't want to go through any high resistance, and they're going to go this way and charge this capacitor. And then once this capacitor charges, it can end up discharging into the neon light. And so, and it's all based on the RC, so whatever the capacitor and whatever the resistance of the resistor is, to create a time constant that is appropriate for how we want those lights to blink. So like I said, besides a blinking light, intermittent windshield wipers are done this way. And again, we like to set the time constant. We come up with a resistor where the time constant is in a range where we want to create that blinking. Okay, and we can change then, if you have a multi-position like intermittent wipers where you can change the time period, they do that by changing the resistance. All right, here's an example problem. A turn signal flashes about 2 times a second. Estimate the resistance in the circuit if there's a 1 microfarad capacitor. Well, since T is about how long of 63% max, we're just going to pretend that that's enough to get a blink cycle on it. And this is just a true estimation. And the signal's flashing about 2 times a second. So we're going to assume we want a T of around 0.5 seconds. Again, we didn't go, you could have gone and made this 2T, because 2T would be a whole cycle. It depends on when we're going to get a blink out of this. But if we say our T is equal to RC, and we say, again, we need a time constant of around half a second, then we can see if we just plug in the numbers that we would end up with around a 500,000 ohm, or in other words, 500 k ohm resistor would be necessary to create that kind of a blink. All right.